Welcome to topic 2b Fermi Dirac integral. So now let's look at degenerate and versus non-degenerate. So what is actually this one? Let's say that you are given this Carrier concentration for 3D devices. We have N3 here, and this is the big capital NC3, which is stand for effective density of states. And then you multiply with Fermi Dirac order of half, and you got eta C, and you move it down here, and you're going to get this Fermi Dirac integral. So in most non-degenerate case, you'll find that when you divide this one, we name it U3, you find it that most of the time cases that you can simplify the Fermi Dirac integral into exponential equation expression like this, exponential eta, and if you move them around eta, you'll get ln U3. But for non-degenerate cases, you do not simplify that into exponential. So what do you normally get is, in over here you have to find out what is this eta Fermi Dirac integral. And in MATLAB, if you take U3 minus f half eta equals to 0, this is called a f0 function of MATLAB. So the f0 function of MATLAB allows you to find this eta when seed value says that eta equals 0 is given. Okay, so you don't have to worry about that. This is just to explain there is a function in MATLAB for Fermi Dirac integral. So MATLAB function file for Fermi Dirac integral, you can download it as fermi.m for MathWorks or NanoHub. It's a MATLAB function for file of half integer value of FDI. NanoHub has another function file, arbitrary index of FDI. It's called fdjx.m. These files are useful in finding average value of various quantity like velocity and energy. So usually for my PhD work last time, what I have to do is that because I'm using, if I want to solve an equation and that equation have Fermi Dirac integral, the integration is very complicated to solve it, but I can get a file which is can downloadable from NanoHub or MATLAB that they can calculate for us. They can just use that file, they calculate the Fermi Dirac integral, you got the value, you multiply, and you got your concentration, as easy as that. So this is telling you there are many versions. You can download for MATLAB. MathWorks is from MATLAB, they are given Fermi.m, but there are also other files. NanoHub provide fdjx.m. Even now, if you just go to Google, you can download Fermi Dirac file. There are many versions. Some versions are quite popular because they can support many etas value. So let's look at this table here. So in exam or in exercises, if you are not able to access a computer, what can you do is that I can provide this table of Fermi Dirac integral. So it's just like a buku sifir, like remember in secondary school where primary or secondary school, when you have to do root square or square root, you cannot use calculator, you have to look at the book, right? So this is the same example. You have to look at the book. So this is the table, how you look at it. So this is the eta here, and this is the order. You got 3/2, -1, -half, 0, all this number here. And this is the eta value for -4 until -1.5 here. And you have to look here in the bracket, there are -2. What are these? These are the power of 10 to the power of -2, okay? And these are the power, okay? And you go to look next one, page 2 here, there are also more values here, and there are more values here lah. So these are the same. If it's 0, which means that is the exact value that you have to use. All right, before we proceed further, I just want to bring you all back to the density of state and carrier concentration. If you look at this density of state expression here, the one that once you solve it, you get 1/2 pi square, then in the bracket 2m star over h bar square over all these things here. Then you get, okay, you bring it down here, and these are the simplified version here, and you got this m star again here. And if you look for 2D, you're going to get something with this m star, and again for 1D the m star here. So what is the value m star that you're going to use? What kind of value you're going to use? So getting back to SQL 3613 here, normally the value that you have to use depending on whether it is a silicon, gallium arsenide or germanium, based on this density of states value here. If you remember, if it's density of state, you're going to use 1.08. That you're going to m star here 1.08 multiply with m naught lah. If it's gallium arsenide, you're going to use this value, and germanium this value. These all are the values that you're going to use depending on you're going to solve it for electrons or hole. What effective mass you have to use? These are the density of states effective mass. Getting back to your lecture note, let me see, this is the one here. Yeah, getting back to here, let me maximize it. These are the table: intrinsic concentration, effective densities of states, and effective mass in silicon. So for silicon, if you depending on the temperature, you're gonna get 300. You're gonna get your Ni, Nc, and Mv value. Okay, this is based on 300 lah. If you get these two value here, and these are the value that you have to use. Okay, this comes from Martin A. Green. Okay, he came up with this table here. So he postulate that if it's for DC here, what's it? Conduction and valence. This is for electrons and hole. Electrons and hole. This is for conduction. We are going to use 1.09 or 1.15. 1.09 or 1.15. Yeah. Temperature here 300. You're going to use this value. And at temperature 4.2, 1.06 and 0.59. And this is the one how you're going to use. If the value is already given here, the effective density of states is already given here, and you are supposed to change the temperature. So what you have to do next is that you have to, what they're trying to do here is that you put this temperature here, similar to last semester, right? But you added this another new bracket here. Okay. Basically what you're going to do here is that you're going to have MO here. You're going to use like one value here, 1.09 MO, and MO here. You're going to cancel each other. That's why you're going to say MO here, and you're going to multiply with this value. Okay. And then that's how you do it. So first of all, you have to find out is this value 2.54. If it's given here, I think the value here hasn't multiplied with this m star yet. Okay, this is value before this m star, which means that if I go back to your this value here, 3D, there's the density of states here. Yeah. Oh, this is not the finished one. Yeah. These are the one lah. So these 3/2, is this the correct? Oh, this is for 1D. We have to go back to 3D. 3D. Yep, yeah, we are back here. So those value that you've seen here, maybe that they calculated before including this m star here lah. So they take out this m star and they put it over here to A here. They put it over here, and then they also take out this temperature, because temperature already include, take out this temperature, and then you get this value. So these are the value 2.86 times 10 to the power 19. So let's look at Neumann's book. 2.86, yeah, there, this is the value that you're gonna get 2.86, and if you still recall 1.04, that's how you get the value. I'm sorry, where is it? 2A2. Yep, this is the one, 2.86 here. And similarly for here, we're gonna go for effective density of state in gallium arsenide. Okay, at gallium arsenide, they're saying that we're gonna look for effective mass. This is the value 0.48 m naught and 0.067 m naught. There you go. This is the same way that we calculate. Again, they take this out and you get 4.4 and 8.3. 4.4 and 8.3. Slightly different. They got 4.7 and 7.0, 7 and 18. Okay, slightly different than here. So just to show you that this effective density of states is very important, because once you already calculated, you derive this equation, but you have to know what kind of if that's effective mass to use, and you look from the table, from the part of effective density of states, you put it down here, you get the value. And these are the minority and majority carrier. This is the carrier, the same thing. Just calculate uncompensated and compensated. What do you mean uncompensated and compensated? Compensated, which means that we have ND and NA together. This one we don't have it together, but this is not gonna in us. Okay, this is the strong degenerate doping. This is important. This one will come out in your test. So this one you just have to look back lah, the previous lecture note. I'm not going to explain how you get that, because you already shown in the table last time. Over here, they are using it. They are trying to simplify it again. And you have kf and velocity. So velocity, I'm not going to ask you lah. Fermi velocity, that's not going to ask you on that. But you have to know this one. How do you get this to strongly degenerate doping? Because I used to ask this for test 2 and also final exam. And these are also microelectronic one, the same thing here. Just want to show you what is the electron concentration. NO stand for what, PO stand for what, ionized acceptor. So if you look back on your Niemann's book, you can try to read it to refresh your memory. These are charge neutrality approximation. What is freeze out? Okay, this is the quasi-low dimensional that I explained earlier on. If you have 3D, your movement in 3D direction, up and down, left and right. This one, you only got movement in X and Y direction. And if you talk about 1D, you can only move in one direction. And all the constant here, like this is missing Z here, right? Z here is going into your conduction band, so it becomes EC2, so slightly raised. And over here, your KY and KZ will be embedded inside your conduction band. It will be slightly higher. So this is what is shown here, lah. Slightly raised. Characteristic in low D dimension. This is the same thing. We are just trying to show you, if you are used 3D here, then if you use this formula here, 3/2 minus 1, you can get your Fermi Dirac order correctly. If it's for 2D here, 2/2, 1 minus 1, you get F0. And if we put 1 here, you get negative half. If you N1 here, you get N1 and Fermi Dirac order, what is that? Negative half. Okay, that's the general equation. This is important. Okay, and this is the effective density of states lah. Effective density for will be ND. Okay, for this example here, not all example will be included in your test here. The Fermi Dirac versus carrier concentration indicates that the electron gas is strongly degenerate when the Fermi energy is 3 kBT above the edge of the conduction band. Find the probability of finding the electrons at the conduction band EC. Find the probability of finding electrons at the Fermi Dirac EF. What is the carrier concentration of electron in gallium arsenide at room temperature at threshold of being strongly degenerate? Sketch the band diagram showing the intrinsic Fermi energy. Fermi energy or this repeated and band gap with approximate value for gallium arsenide at room temperature. So again, for those that haven't taken SKEL 361T, these are the basic. These are the refreshment course. You have to know all these things here. So let's look at the answer here. So basically, you just, how do you going to solve it? You are going to use the Fermi Dirac probability function, and you just put the value in here, and you calculate what's the probability to find above. The probability is above conduction band. The probability is almost 1 lah, 0.999. This is the Fermi Dirac probability distribution function. You just put in all this value and calculate, you get your answer. As simple as that. 1B. what is the probability at EF? Just put EF minus EF, get 0 here. 1 plus 1 plus 1 is 2, half. Okay. What is the carrier concentration in gallium arsenide at room temperature? So this one, the one that you can find from the table calculation here, you get this NC3 4.4 times 10 to the power 17, and then you multiply with this value, you get your answer. And for here, N3 19.7, what I'm trying to do is they're trying to change the unit. Okay, then from the table you get this 4.48. But how do you get this 4.4 times 10 to the power 17? This is the one. Let me check back how to get 4.47 gallium arsenide. Is it given in the table or not? If it's not given in the table, let's see. Is it something like this here that you have to calculate? This is for silicon. There, 4.4 times 10 to the power 17 cm here. This is the equation that they put in here. They calculated 10 to the power 17. Sorry, getting back here. There, 4.4. Okay. So if that equation is given, then you are able to calculate this and you put it in, and then let's look at the table and you get it. Okay, so I have to recap again lah. Let me think about this. If I'm going to include the Fermi Dirac order definitely coming out. If I were to include here this NC3, will I ask you to calculate or not, or I'll just give you a constant and you can just plug in and get it answer. So these are the Fermi Dirac integrals just now that how they get the value 4.4876. 4.876. Okay, as easy as that. Put it in here, get the value. And the next one is the Fermi energy versus carrier concentration. Indicates that the electron gas is strongly degenerate when the Fermi energy is 3 kBT above the edge of the conduction band. So this is just sketching only. Sketch the intrinsic Fermi energy band gap with appropriate value for gallium arsenide at room temperature. So this is okay, straightforward, not difficult. And if you see something strange here, is that the Fermi energy is 3 kBT above. Okay, slightly higher here, and then you have to know what is the band gap for gallium arsenide, and then you can do it. Intrinsic, let's say intrinsic is exactly in the middle, 1.42. Intrinsic, you divide by half, 0.71, 0.71. Okay, following the same procedure, derive the expression intrinsic velocity for D123. Okay, the velocity, like I told you, it's not coming out, so you don't have to worry about that. This is the answer. The general intrinsic velocity is given by this equation. There. What we're gonna do is we're gonna do degenerate and non-degenerate. We're gonna stop at concentration. There will not be velocity. And here, this is energy. Of course, energy is not covered. This is the solution if we were to do energy. Effective density of states. This one is similar to SKL 3613. You just calculate here, nothing new. NCNB, you calculate, you get the value. What is the ratio? How about this one? I think this one is also straightforward, not difficult. It's similar to SKL 3613. You just use your equation here, you can calculate and you can get your Ni. If it's a compensated, first of all you use this equation, and then the next one is use Ni squared divided by your value, and you're going to get your answer. Example 6 is on silicon doped with boron, find NOPO. Okay, straightforward as well, not that difficult. Got the NO, you can calculate, and then you find your, you have to find your PO. Did I find my PO? Oh yeah, I say because we included non-ND material, non-degenerate and complete ionization, then you get exactly this PO, and then you calculate and you get this. So for those that have not taken SKL 3613, you may find that this is a bit something new to you lah. But don't worry, because if you were to come out in your test or final examination, I will let you know in advance, and whether you should go through the the book or not lah, the Niemann book. Okay, with that we'll end this lecture for Fermi Dirac integral.